Let's try this. Forgot to do my sanity check. Let that run. Okay, good. We're good to go. We're all wired up. Okay. So today we're going to cover just some function practice, as the slide suggests. We'll just do some code alongs and just some function practice. So I want you all to get your environments ready to code along with what I'm doing. And feel free to, this is sort of a, treat this as a bit of a forum, ask me, stop me if something doesn't make sense, or ask in the thread, and one of your fellow students may give you an answer. And feel free to, chime in and answer other people's questions, so I might not see them right away. If you do want me to specifically see it, just do @Clark, whatever the whole handle in front of it, and I'll see it sooner. So, okay, so function practice 2. So this is, this lesson I think is kind of meant to kind of work off of function practice 1. So it's been a while since I've taught. I forgot to mention this. This is if you look in the schedule, this is going to be my last full class with y'all. So, it's been a lot of fun. I've enjoyed working with everybody, and, I'll see you on Saturday. I'll probably be in there with Tovio, and I'll be around. You're all welcome to DM me if you need any help with Python. Tovio, I'm sure we'll mention this at some point as well. We'll probably talk about this on Saturday on the last day of class. But our model for premium prep is a little unconventional. We mentioned this a number of times before, but I think it's just nice to kind of reiterate it and mention it again. The model is that you get into premium prep and you can stay as long as you need to in as many premium prep cohorts as you need to, and you don't have to pay again. So, if you need to take another round of premium prep, the course is designed to go fairly fast, but since we allow you to just take it in succession as many times as you need, that's sort of how we deal with it going fast. So you're welcome to take it again. I'd love to have you back if you need it again. And yeah, just I think there's a deferral form that might be pinned to the channel. If you can't find it, DM me or Tovio, and we'll get it to you as soon as we can. Yeah, and that'll probably be posted in the main channel as well. So yeah, I just wanted to mention that. So if you feel like you need to stick around, you're absolutely welcome to do that. Okay, let's actually get into the material here. So yeah, this is meant to kind of bounce off the previous functions practice. But even though it's been I guess a week since I taught last, but that's okay. So some of this might be referring to previous things. So anyways, remember coding the PMF function, the binomial PMF function. Let's now create a function that will return our CDF. I'm assuming Tovio's gone over the CDF with you. Can somebody confirm that? Thumbs up in chat or on camera. Have you covered the CDF? Okay, good. I was talking with Tovio the other day, and I was like, I didn't realize that our schedule kind of got moved around a little bit. So when I did the lecture on classes and we went over coding the binomial distribution, I was like, I know you went over this with Tovio already, and then I just threw you into a binomial distribution. And then I talked to Tovio afterwards, and they said, they were like, oh, we didn't go over binomial distribution yet. And I was like, oh, oops. So that was a little bit of a miscommunication just due to swapping some days around between Tovio and I. So yeah, anyways, but we definitely coded that out. I'm sure you've coded out or seen Tovio go through binomial PMF and CDF. So we're going to build out the PMF and the CDF. Let me see where I was. Create a function that will return our CDF for a binomial distribution. A problem for the CDF might look like something like this. Suppose you have a fair coin, meaning you have an equal probability of either side coming up, and you flip it 10 times. What's the probability that there will be 6 or more heads, 6 or more successes as a result of these 10 flips? So we want to represent the below formula in Python, where n is the number of trials, k is the number of successes. Well, that needs to be corrected actually. In this case, as shown in this formula, I is actually represented by the number of successes because this is a CDF. And yeah, so it's kind of funny. In a PMF, k is the number of successes. In the CDF, most of the time, the way we write it, k is like the limit of the range, and then I supplants k for the PMF portion of it. So I is the number of successes, and p is the probability of success. Okay. So there's a question in here that I wanted to ask. Let's see. Yeah, so here's our question. I'll just copy this in. If I can operate my mouse here. Okay. Suppose you have a fair coin, you flip it 10 times. What's the probability that there will be 6 or more heads as a result of 10 flips? This is a bit of a side point. Doesn't tie in quite directly, but I want to get you all, thinking about this, and I want to sort of, bring some context to this. And I'm not sure necessarily what Tovio's covered around this, but if I flip a coin 10 times, you don't have to know the exact probability of each whatever outcome. If you can do that in your head, then I'm sure I have a lot to learn from you. But in this case, what is the most likely outcome? Go ahead and put it in Slack. Oh, sorry. Maybe I didn't make that clear. So, given the premise of this this question, right? We have a fair coin and we flip it 10 times. What's the most likely number of successes, of heads? Yeah, there you go. Cool. Yep. So imagine we have an unfair coin. Let's say there's a 70% probability of failure. So what's the most likely, or what's the highest probable number of successes? Right, exactly. So I like this question because it really brings a binomial distribution sort of down into like reality. This is a pretty intuitive thing. Deriving specific, quantitative answers about, you know, the exact probabilities is a bit of a different story, but you know, that's I like that question just because it shows something about statistics that I often find to be true, which is it's often the formalization of ideas that are generally pretty intuitive. Cool. Okay, so we want to represent that formula in Python. So this is written with a sigma. That sort of sideways M is a sigma, which I'm assuming you know. The number on the bottom just defines the term I and says we started at 0. And the number at the top is the upper boundary of the range. So who can tell me, when I see a sigma, who can tell me how to translate a sigma into code? And there's a few answers here. Some, yeah. Yeah, sigma we usually think of as, well, I mean, sigma, yeah, means sum. Summation plus equals for loop, yeah. So when I see a sigma, I think, well, I can write a for loop, you know, from I equals 0 up to k is for I in range k, for I in range k plus 1. And I think the square brackets means that k is included, so. Yeah. So let's do this. Let's start with our test. So we'll take in P, and K. Actually, I'll do N, K, and P. And I'll default P, so I won't even pass it in. We'll just do N and K. So we'll say N equals 10, K equals, so what should my K be equal to given this question from my CDF? 5. So suppose you have a fair coin and you flip it 10 times. What's the probability that there will be 6 or more heads as a result of the 10 flips? Yeah, so I forget that this is actually 6 or more, so we have to do 0, 1, 2, 3, 4, 5. Yeah. Apologies. It'll be 1 minus K is actually 5 in this case. So we'll do 1 minus this equals the probability of getting 6 or more, because it's the probability. If I add up all the probabilities, you know, the probability of getting 0 and 1 and 2 and 3 and 4 and 5, etc., all the way up to n, then that probability cumulatively is 1. So that's the whole space. So we can say 6 or more is like saying 1 minus 0 to 5. The way we build a CDF is we start at 0 and we go up to an upper bound k. It's Python, you know, it's programming, so you could build this with like lower and upper. if you wanted. Maybe we could rebuild it that way. Sometimes I like to do that because, I don't know, I'm more a programmer than a math person. I'm like, I'll just do it the easy way. It's my code. So, okay. So I am doing this in a particular order. And I know I mentioned this before, but I don't want this to just get ignored, So I want to be clear about why I'm doing things in the order that I'm doing them, right? So I didn't start with a definition. I started with a call. So there's a question here. Who can tell me why might I start with a call? There's a few reasons. There's a few, in my opinion, like good reasons. So why would I start with a call instead of a definition? And then this question here, to clarify, is k equal to 5 because 6 is not included? So the question is, and I kind of made a mistake here when I was writing this test because I was going to test 0 through 6 inclusive. The question is not 0 through 6, it's 6 through 10. The probability of getting 6, 7, 8, 9, or 10. Right? So it's the probability of each of those results added together. So 6 is included, it's the lower bound. So when we say 1 minus the probability of getting 0 through 5, that includes 6 by omitting everything that we're actually trying to calculate for. Does that make sense? And then we got a couple answers here. To have an end in mind before building anything. Yeah, that's a good way of saying it. Yeah. You work out of, you work out the parameters you need for the function definition by writing out the function call. Yeah, exactly. I think both of these are probably better ways than I've been saying it, frankly. Yeah, like feel free to put this in your own words too. Like, write this out. Take a note here. Why do this first? Both of these are really great explanations. Working out the parameters. So the way I like to think on that note, the way I like to think about it is like, I need a tool and I know how I need the tool to work. So I'm gonna like pretend like it exists and implement it in the way that I need it to work. And then I'm gonna I have a clear destination in mind. That's gonna prevent me from like, oh, well, why don't I add this? And why, while I'm here, why doesn't it do this? And I could have it. And then you have something that does everything kind of, but nothing really. So helps prevent, scope creep and things like that. Helps keep things clear. So, and then all we got to do, it's simple, nice and easy. All we do is just justify having written that by writing some code up here. So binomial CDF, we'll take in N, we'll take in K, and we'll take in P. And since I'm not passing P here, what might I want to do up here on line 9 in order to rectify that? Well, I'm assuming P equals 0.5. Tis called method stubs. Stubbing out your functions, indeed. Yeah. It's the right thing to do. Well, in my opinion, I think there are plenty of other good working workflows and way of problem solving, but this is certainly what works for me. Cool, yeah. Okay, so P equals 0.5. So this is this is called a default parameter. And this is how we can tell Python to make an assumption. Like, hey, if I didn't pass anything, any value for p, just assume that I wanted to use 0.5. So back to this sigma. So that's going to be 4i in range k plus 1. We want to include k. Then we're going to, it's a sigma, so it's a summation. ACC equals 0 plus equals, or plus gets, PMF and KP. NKP, return ACC. Now ain't that just a simple little accumulator pattern problem? That's all a CDF is. You can write any CDF like this. You know, if this were Poisson or any other CDF, you write like this, and then you're just doing the appropriate PMF for that one. Obviously, this is not going to work because we don't have a PMF. So let's start implementing the rest of this. So I'm just going to use this as, you know, like this is my test for the CDF. I'm just going to use this as the test for my PMF. Def, PMF. I mean, same thing's happening, right? You know, maybe I should write like its own test or whatever, but same thing is happening because I'm utilizing it in the way that I intend to utilize it in an actual function here. So we're going to take in NK and P again and default P to 0.5. And then we're going to return combinations N and K times P to the K times one minus P to the N minus K. Okay, so same thing here, right? I have combinations. I haven't defined combinations yet. So we're just gonna, we're just gonna go up until we have all the functions that we're calling. And this is a fairly, I like working in this way because this is a fairly typical reality of problem solving where, you invent the way something should work and then you make something that works like that. It's great. Def combinations. I'll take in N and R. You can call it K or R. And we'll return int of factorial N over, now, this is a funny thing, but recently I forgot these parentheses right here. Like 5 times I've written a combinations function on stream or in class, and it's really funny because I just keep forgetting it, but never again. I'm learning the hard way. So don't forget your parentheses right there. So, and I am casting this as an int, right? It's going to give me a whole number anyways, but since I'm doing division here, it's going to give me a float. So I'm just going to cast it as an int because that's what I like to do. Yeah, so factorial N over factorial N minus R times factorial r. Cool. Same thing for factorial. Factorial n prod times gets I, return prod. Oh, need to replace K with I in the PMF. Thank you. Good catch. Nicely done. Yeah, so just out of habit, I'm thinking binomial PMF takes in NKP. And yeah, in here, when I'm invoking it, obviously I do need to do NIP. Yep. This is a perfect example of the benefits of pair programming, why it's catching on. You know, two sets of eyes are better than one. Cool. So there we go. So I wanted to kind of just move through that in that way. Like, hopefully it's clear, you know, and I really want to kind of push people towards that workflow, right? And it all starts here, and it's kind of weird because it feels like working backwards, because it is. But I think this models problem solving, and a lot of times in the real world, where you encounter a problem and you know what you need to do for your solution. You can sketch that out right now, right? Like, I know in order to do a CDF, I've got to, I've got to have something that looks like this. I pass it a value for n and k and p, etc. So yeah, and then this necessitates that we write the CDF, which necessitates that we write PMF, which necessitates combinations, which necessitates factorial. All right. Suppose you have a fair coin. You flip it 10 times. What's the probability of getting 6 or more heads as a result of these 10 flips? Yeah, this is just going to go through exactly what we just did. Cool. Now, we've got a question here. Instead of writing out the function for factorial, can we use from math import factorial? Sure, but for the sake of like, well, sure. If you're new, I would just say write out the factorial function. Just gets some code under your fingers and gets you writing it. I'm a little bit predisposed to like write a tool before using an already built tool, and perhaps that's a shortcoming. So take it with a grain of salt. You do whatever works for you. But yeah, math.factorial would work. Okay. Is this just CDF probs? Yep. Okay. Yeah. Okay, so just make sure we didn't miss anything here. So suppose you have a fair coin, you flip it 10 times, 6 or more heads, So that's 1 minus the probability of 10 of getting 0 through 5, which is 0.3769, 0.37695, etc. Okay, cool. We got the right answer. And this is just another example of that, just to kind of reinforce, like, mechanically what is happening with a PMF. Excuse me, a CDF. CDF equals this. Well, yeah, let's do it like this. So this is one way to look at it. However, what we're actually doing is 1 minus all of this, where we have 0, 1, 2, 3, 4, 4, and 5. So mechanically, this is more along the lines of what we're actually doing. Yeah. Either way of looking at it, though, it's just fine. Okay. So let's use our functions we've created to see if we can answer the following problems. An article, should you report a fender bender, from Consumer Reports, September 2013, reported that 7 in 10 auto accidents involve a single vehicle. And just a disclaimer, the article does recommend that any accident involving more than one vehicle should always be reported. But evidently, this is according to their statistic, 7 in 10 accidents involve a single vehicle. So suppose 15 accidents are randomly selected. So we have a sample size of 15. How would you calculate, or how would you call the function to get the following answers? And I will put these into Slack. Actually, just pull them in from the markdown. Oops, I can't do that. They have the answers. Okay. I'll just put a couple minutes on the clock here. Feel free to just put in your answers for these. Okay, I'm not seeing any answers in Slack, so I'm going to assume people need another couple minutes on this. Feel free to put any questions you have in the thread. Okay. Go ahead and get in your answers, whatever you've got. It's okay if they're not quite finished yet. Excuse me. Okay, so there we go. So how can we calculate the probability that exactly 4 of the 15 randomly selected accidents involve only one vehicle? So for this, let's see here. One second. Wow. Okay. So for this, we can do our binomial PMF. We can do our binomial PMF The number of events is 15. And we want to know, so a success is that a vehicle or an accident involves only one vehicle. So we want to know the probability of getting exactly 4 successes. Given from our previous example, a rate of 7 out of 10, which is 0.7. So that's 70% probability that the accident has only one vehicle in it. Oops. Oh, there we go. Okay. And then what's the probability that fewer than 4 of the 15 randomly selected accidents involve only one vehicle? So this is going to be our CDF. 15 up to and including 3, because 0, 1, and 2, and 3 are all less than 4. Probability of 0.7. Okay, let's run that. All right. There we go. So what's the probability that 10 or more randomly selected accidents only involve one vehicle? So for this one, we can do 1 minus the CDF, 15 events. Wait, so this is the probability that 10 or more randomly selected accidents, 10 or more, okay. So that'll be 1 minus 0 through 9, yeah. Oops, 0 through 9. Okay. And then what's the probability that more than 5 and less than 8 of the 15 randomly selected accidents? So this one, potentially, we could fudge a little bit, right? It's a descriptive fudging, right? It's going to be very clear. So we could say PMF of 15 more than 5 and less than 8. So that's the sum of 6 and 7, right? So 6 and 7 plus, oops, that's 0.7. And then we'll just change our K to 7 here. And then, well, we don't need to save that at a variable. We'll just stick that right in there. Cool, okay. So function breakout 2. So changing gears, let's create a function that takes a list of words and returns a new list of words that are anagrams of each other. And okay, this is kind of worded strangely. So we've got a totally different problem here, totally new problem. Let me get this straightened out a little bit. Okay. Okay, so this is our input list. And this is our expectation for this problem. So I'll start off with my test. Anagrams. We'll take an input list, and we expect this. So what this means is it's going to look for words that have an anagram in the list. So to be clear on this, an anagram is two words are anagrams of each other if they share exactly the same letters. So what I mean by exactly the same is not only the same letters, but the same number of those letters. So let's see, what's an example? Like cat and act. So cat and act are anagrams, right? Because they both contain one C, one A, and one T. If I had like TACC, right? This contains all the same letters, but it doesn't contain the same amount of them, right? So, and then TACK obviously contains a K, right? So the output list is going to accumulate. It's going to accumulate words that have an anagram in the list, as long as it's not itself. So we won't consider a word an anagram of itself. So if, let's say, if dog appears in here twice, we don't want it to appear in there on that basis. Of course, dog and God are anagrams, so those will both appear. But let's see, tack, right? If tack were in here twice, and let's just put it in there twice. So tack can't be considered an anagram of itself. Okay. So fun fact, this used to be a long time ago when I first started doing this job. This was our TI was broken into a Python TI and a stats TI, or two TIs that people needed to pass before we unified the TI. And this was our first Python question. So I have fond memories of this problem, but the TI has evolved a lot since then, so it's not really the same. But yeah, okay. So anagrams is going to take in a list, and we're going to return a list. So let's actually create a list equals empty list, and I'm going to call this array, ARR, like this. Okay. Cool. So that should just return us an empty list. See where they're going with this. Okay. So let's think about this. I'm going to kind of try to crowdsource this a little bit from you all. we will need to iterate through the input list in such a way that we compare every item to every other item and see if they contain the same letters, as long as they are not exactly the same word, right? So we'll start with, how should I demonstrate this? Like, this algorithm could look like this, right? Where we have, first we want to compare dog to every item in the list, right? So first we're going to compare it to dog. Well, this is not a valid comparison because obviously it's the same. So we don't want to do that. So then we're going to compare it to God. See, does dog and God have the same characters? Yes, in fact, they do. So we can say that dog is an anagram. Well, we can say both of them are. In this case, we could just pick one or the other to add into the list, because, you know, later we will compare God to dog, and that will add in God. So if we add in one or the other or both, then we're good to go. Okay, so we compare dog to God, and then we're going to compare dog to cat, and then dog to act, et cetera, right? Till we get to the end of the list. And then we'll come back up here and we'll advance this one. We'll compare God to dog. Now we don't want to compare God to God because it's the same thing, obviously, and God to cat, and God to act, et cetera, all the way to the end of the list. And then we'll advance this, right? So hopefully that's clear, but that's sort of a sketch of the algorithm that we're going to use. If you have any questions about that, go ahead and put them in. But I'm assuming that is clear. Cool. So how do we do that? The question is, and this is a good way, you know, as you're solving a problem, like you're trying to solve the problem, but you're like, think about it like little milestones, like what kind of smaller problems is this larger problem made out of, right? So there's the how do you compare everything to everything else problem. That's the one we're on right now. Then there's the how do you tell if a word is the same as another word problem. And there's the how do you tell if the word is an anagram to another word problem, right? So that's 3 problems, and we could add a couple more. We'll think about this and add a couple more goals in, but that's an example. So we're on the how to compare everything to everything else. Compare every item in the list to every other item in the list. So think about this. Go ahead and go ahead and put in an answer, or a suggestion, or a guess. You know, it doesn't have to be code. It can be, you know, a question or whatever. I'll let y'all think about this for a minute. So we've got a suggestion to do a membership check That's a thought. Any other suggestions? List 1 equals list 2. So I see that, and I think perhaps like you're thinking about checking if 2 of the words in the list are the same, and yeah, there will be a time when we're going to check that. I just realized perhaps my question could stand to be clarified here. I guess what I'm asking is, how do we, like, first we need to get, before we even do the comparison, we need to get access to every combination of 2 words, or every permutation actually of 2 words. So we need to be able to, I mean, I guess I could put it like this, like, I should have kept that example around. Like if my goal was to print out, oh my gosh, was to print out the words in pairs, like dog, dog. Obviously that's, we'll handle that in its own case. Then dog, God. Then dog, cat. Oh, come on. Cat, act, tack, star, rat, rats. Right. So I just, like, the first question really is like just accessing every combination like this, right? And then we can just do, oops. No. We'll do this. God. Then we'll do, oops, this, cat, etc. Right? Len word 1, word 2. Yeah. Okay. Loops. Ah. Okay. Look at this. I missed that. Apologies. Forward 1 in array, forward 2 in array. There we go. That's what I was looking for. So this is going to give us access to each word and allow us to compare it to every other word. So forward 1 in array, forward 2 in array, print. Actually, I'll do this. Print word 1, word 2. And in here, I'm actually just going to add some spaces. 1, 2, 3, 4. Bingo. Oh, and then this is going to give me syntax errors because stuff. Of course, it hates that as well because there's a space in front of it. So I'll just comment it out. Okay. So now I can print out everything for everything else. Now we can actually get, and I apologize because I framed it in terms of comparison. Really how I should have framed it is in terms of access. We just need to access each word for every other word in the list. And that's what this allows us to do. Now we can start with the comparisons. So for this one, I see a number of suggestions. Sorted. Yeah, I see a lot of good suggestions. Cool. So now we can actually do some comparisons. So let's just make sure we're not going to compare a word to itself. So basically, I just want to make sure word 1 and word 2 aren't the same word. So if word 1 not equal to word 2. Now I want to see if they're anagrams. So how could I tell if the two words, we know they're not the same, but how could I tell if they are anagrams of each other? What's something that I could do? CH in words are equal. Yep, characters in words are equal in value and in quantity per each value. Sorted elements. Yep. Yeah, so that's a great suggestion to sort. So that's what I prefer to do. So if sorted word 1 equals sorted word 2, here list dot append. We're just going to append word 1. Okay, cool. So we get dog, god, cat, act, star, rats. Dog, god, cat, act, star, rats. Cool. So let's do something. Let's throw a little curveball here, and let's add in another dog. Okay, so we got dog, god, dog, cat, act, dog, star, rats, right? So in this case, we've got duplicates. Dog and god match twice because there's 2 dogs. So yeah, that's what's happening there. So those both end up being doubled. Yeah, so how can we get around that problem? We could use a set. How could we get around it without using a set? Although a set is a valid thing to do here. Count? How would you use count? Yeah, there you go. So we could see if it's in the list before we add it. So if it's not in the list, then we'll add it in. Yeah, there you go. Yep. Cool. Now we've got these sort of, I just think this function kind of looks, it's so swooped. So we can actually kind of unindent some of this. In this particular case, we can treat these as ands. Oops. Like this. I always forget if this is going to give me yeah, I got to put backslashes on the end of the lines. So sometimes I like to break up my lines like this if I have sort of longer conditions. with like ands or ors or something like that, I'll break them onto multiple lines, and that usually makes things kind of more readable. So you can do that, just stick a backslash at the end of the line, and that'll tell Python to ignore the line break. How do you know when to use and versus nested if statements? So to be clear, this is logically identical to this. One doesn't do something that the other doesn't do, but you know, it's an aesthetic preference, and it's a stylistic norm. The way you can tell to do this is if we look at this. I mean, if you look at this, you could almost describe this as if the words aren't equal and their sorted versions are equal to each other and the word is not in the list, then add it to the list. So when you see a pattern where you have something that you're doing, this is your consequent, right? This is the consequent only when all of these are true, right? And that's the brand, that's like the thumbprint of an and, multiple conditions. So if you have, I want to be clear about this because I think you all have heard me mention this before. I mentioned it a few times when we were initially talking about control flow. There are patterns that you can recognize. This is one of them. Like you have these nested ifs, and we can simplify that and make our code, you know, more idiomatic and nicer to deal with by using and. So this is a pattern, but don't like always be a little bit wary of like consistent axioms in regards to if statements. Be careful about developing a rule of thumb with this because situations are unique. Now, in this case, there isn't a scenario in which doing and is different than doing this. There are cases in which you will need to have an if immediately within an if. If the inner if, I know this is like if the if, but if the inner if has an else to it, that needs to be its own set of conditions, or an if, or an else, or an elif, right? Because that alternative might only apply to one of those conditions. The other scenario is if I need to do something here, but then check this condition, then I need this to be its own condition so I can do that special thing here and then check this other condition in here, right? So it might be like, well, if the sorted words are equal, I know there's something I want to do regardless of whether or not it's already in the list, right? So that's another scenario in which nesting is still necessary. So this pattern only applies, pattern being that you can, or well, this rule only applies to the pattern wherein you have solitary ifs, meaning that there's no alternative, alternative being an elif or an else to them, right? Solitary ifs immediately nested in each other with no other code. In that case, you can do an and. So that's the pattern. The easy way is if you can read through it and say, if condition A and condition B and condition C, oh, I can just use and, right? But I just want to be, I see a lot of people get tripped up on like, oh, well, I'm always going to write my control flow this way, and it gets weird. Okay. There you go. We're a little past halfway. Let's take about a 5-minute break. Let's reconvene at 21 after the hour. And we're back. Cool. Cool. All right. Let's move on to the next one. Let's just go through this, scroll quickly through the anagrams thing, make sure there isn't anything cool that we should look at first. No, okay. All right, so let's create a function that sorts a given string where, okay, let's do this. So it sorts a given string where each word in the string will contain a single number. So that's these ones. Okay, so we've got some tests here. And let's see. Oh yeah. Let's call this order. Take in text and pass. Okay. Oops. Of course I didn't comment those out. There we go. None. That's what we expect. So where each word in the string will contain a number. This number is in the position the word should have in the result. Numbers can be from 1 to 9. The first number will have a 1, not a 0 in it. If the string is empty, return an empty string. So that's our edge case here. Oops. String is empty, return an empty string. And the words in the input string will contain only valid consecutive numbers. Okay. Cool. So this one's interesting. It has something to do with a very particular mechanic unique to sorting a list of tuples. So we'll come back around to this. We're going to kind of build up to this, but I want to talk about this because it's a very particular behavior, and it's a useful one that actually comes up. So if I have B, let's do that, something like that. So the question is this list sorted? And there is a yes or no answer to this, at least so far as Python is concerned. A better question might be, does Python think this list is sorted? If I sorted this list, what would happen? I mean, this is the perfect kind of thing where I usually ask a question like this, and then I'm like, aha, I got you, but it's like, obviously it's going to give you an error. And you might think, oh, it's going to give me an error, because what does it mean? I can hear me saying, like, what does it even mean to sort a list of tuples? Well, turns out there is a meaning. There is a consistent thing that happens. So when you sort a list of tuples, it ignores everything in the tuple except the first element of the tuple. So in this case, the tuple contains an alphabetical character, so it's going to sort lexicographically according to the first character of the tuple. Now, when it sorts, it's not going to do anything weird to the tuple. It's not going to sort the tuple. It's going to sort, well, it's not going to sort in the tuple. It's going to pull the entire tuple to the position of wherever its first element should go in comparison to the rest of the first elements, right? So if I sorted this, so remember B with 0 and A with 1,000,000, right? So A comes first and B comes second. And the numeric ordering here has absolutely nothing to do, like, just to really drive this home, sort is utterly unconcerned with anything other than the very first element in each tuple. So that's, like, you could think about it like that's the sorting handle. That's the thing it grabs onto, is the first element in the tuple. I say a list of tuples here. I suppose I should clarify this, like a list of lists or a tuple of tuples or a tuple of lists or whatever. Usually we describe this as a list of tuples like this, but it could be anything really. Anything that sort of has that shape, that two wide or in wide array or matrix shape. But yeah, so that's what's going to happen if we sort a list of tuples, and we're going to come back to that. So for now, we've got other smaller problems to deal with. So order takes in text. We've got to iterate through each word of the text. Who wants to help me out with this? How do I iterate through each word of the text? Dot split. Yep, dot split will help me out. For loop, I wouldn't want to call it loop, but I would call it word. For word in text dot split. Yeah, so this will give me, let's just print word just to verify that that's what we have. Cool. So there's our words. So now I have to discern which number is in, well, I have to discern which number is in each word. And I need a place to save these. I also need like a frame of like a schema, really. I kind of spilled the beans with tup list. equals list, right? So we're going to put tuples in this list, hence the name tuplist. The tuple will contain who wants to tell me what they think the tuple is going to contain, given where we're at in this problem? How might, not just what it might contain, but you know, what the types are and what the elements are. So number from word as an int, and word, the word itself is a string. Yeah, exactly. So that's how we're going to structure each tuple, right? So we're going to be putting that inside of tuplist. So first we've got to determine what each number is in the word. And we're going to assume that every word has a number. We're just going to make that assumption for now. So how do I determine what the number is in each word? How might I go about doing that? For num in word, right? So for num in word, this is good. This is on the right track. Careful about your variable naming, because this suggests that every element in the word is a number. Every element is, I mean, we could call it L to be safe. I would say it's a character. Some of those characters might be digit characters, right? So that's not that big a deal. I mean, just one thing like that, you can work around that. But it's the kind of thing like it can become confusing. Like you get distracted and then come back to the problem, and you look at num and you think, oh, this is an integer, and it's actually a character in the string. So yeah, just something to watch out for. But right idea, totally. So for the character in the word, how can I tell if the character is a number? Oh, if char in, yeah, we could do a check for membership. Somebody's suggesting is alpha. Type is always going to be a string. Let's prove that. Because here's the thing, we can cast it as an int once we're sure that it's castable as an int, which means it's a digit character. Let's just verify this. That's class string. There we go. Those are always going to be strings. So it's good thinking though. So somebody suggested a check for membership if ch in a string of 0 through 9. We could do that. There's a method though that's really straightforward. Oh yeah. Okay, so somebody's suggesting is digit. Yep. If ch dot is digit, right? So is digit gives us a Boolean value as to whether true or false, whether ch is a digit character or not. If it's not a digit, then we don't care. If it is a digit, then let's do that append thing. So let's say tuplist dot append the tuple containing an int of ch, and then we'll do the whole word. We also don't need to check any other, we also don't need to do this inner loop anymore. So let's just break the loop as well, break. So we'll append, and then break. Everybody get that? Everybody get why I'm doing a break there? No is an acceptable and encouraged answer if the answer is no. Okay. Okay. So it's going to work without the break. We don't need the break, but it's going to save us from doing work that we don't need to do. As a constraint to this input, the input is a string of words where each word definitely and always contains one digit between 1 and 9. That's it. Each word contains a digit character in it, just some random place in it between 1 and 9. Okay. Excuse me. So once we find, if we say if ch.isDigit, once we find that digit, we can append the tuple containing the digit and the word. So we can append that whole tuple, and then we don't need to continue searching for the digit. We're done. We found that digit, so we can break the loop, right? So it, like, take people here, right? PE6 opal. People with a 6 in it. So we check P, if P is a digit, P is not a digit. E, is E a digit? It's not. 6, is 6 a digit? Well, it is a digit. So we don't need to go continue checking O, P, L, E to see if they're digits as well. We can just break this inner loop, and this is going to save us some unnecessary loopage. Cool. And you might, I think it's also easy to look at this and say, hey, wait, you have a break. Why isn't that going to affect the outer loop? So break, just, you could think about it like it's going to go up and find the first loop that it's inside of, and it's going to break that loop, right? So it's most immediately in this inner loop, so it's only going to break that inner loop. It's not going to break the outer loop like that. Cool. Excuse me. All right. Okay, so let's see what we have so far. Okay, so our input string, let's just do one test. Our input string is with a 2 in it, this with a 1 in it, test with a 4 in it, A with a 3 in it, and we should expect this as a test. Currently, we're getting 2 is 1 this, 4 test, 3 A. So we've made a step in the right direction, but somehow it seems like we're further off an answer than when we started. However, I'll just do this here for now. Sorted. This is a test. So if I sort this, it puts them in the right order. Now the problem is I've got a list of tuples with a digit in the first place, and I only care about the second part of the tuple. I want those to be back into a string separated by spaces. So I actually don't want to return top list here. I kind of did this later. I kind of got in a few lines before I wrote in tuplist. Usually I'll think about what am I returning, and then I'll return it right away. And I want you to, this is a good moment, because I was like, okay, well, we'll just return tuplist. We're not actually going to return tuplist. Look at tuplist. Sorted tuplist is nowhere near what we need this to be. So we're not going to return tuplist. We could make this into a comprehension. and do something that way, but I'm going to do this in a for loop. So we're going to return something else. We're going to have a second accumulation stage here and return something else. So I want to be clear about this. I kind of encourage a lot of patterns that are like, don't worry about it. And it's not because I don't care about like writing good code. It's because I know problems will sort themselves out if I just keep pushing through, right? Like there's a lot of times where it's like, well, I could like sit here and really like be like, super mega smart thinker and like brain it all myself. And even if I'm like a super genius, I'm probably going to be slower than the computer at figuring certain things out. So there's certain things that you can just fudge and guess at. And then as you get into the problem, it'll become clear, and it's not hard to just change that midway through the problem. So I'm taking a minute to note this because it's a really useful pattern that can help make you more productive when you're trying to do lots of problem solving. Allocate your thinking time and energy to places where it matters. When I'm thinking about what to return, really I just want to return something that might kind of give me an idea of what's going on in my function. And usually I end up returning that thing anyways, but in this case, that's not the case, not a big deal. So we'll iterate through this for num, I'll call it n. Let's call it num for num and word in tuplist, sorted tuplist. Now, what do I want to do? I think I'll just be ultra lazy and just call this list. That's nice. So let's just do list right here, and then list dot append word. Cool. Okay, cool. So this is an extremely simple accumulation. Like there's nothing dynamic going on here. Something like this where I look at this and I'm like, this is like almost pitifully simple. It's not even worth making a formal accumulator. We'll just do this is a perfect candidate for a comprehension. Nice simple accumulator to turn into a nice simple comprehension. Okay, so there's our list. We know we've got our list. So we're still not there yet, but from here, we can do string space dot join list. There you go. So that's pretty easy. And if I wanted to, I could even put that comprehension right in here, and I don't even need to worry about that, right? So I don't know, to me that this is two very simple lines of code. This is one not terribly complicated line of code, but it's getting a little dense. If I were actually writing this is what I would do. What if CH has more than one digit? Or what if character has more than one digit? Given the constraints of this problem, we're assuming that's not going to be the case. Like we're assuming that there's not going to be a 2-digit number. This function will not handle that. And that's just part of the constraints of this problem. It would be interesting to write this in a way that's capable of handling like a multi-digit, like an 11, or if you have a string with 15 words in it, you have 0 through or 1 through 15. Like entrenched in thinking in 0-based indexing, and I'm like having a hard time thinking in about 1-based indexing. So anyways, yeah, it's just a constraint of this problem that we're assuming it will only have 1 digit in it. But you could see if you could write it in a way that it's robust enough to handle 2. Cool. And then let's see here. That's a typo. Can't append two things. You know what? I probably went in there and like cleaned that up and was like, what's this double parentheses doing here? And I like induced a typo. Sometimes I do silly things like that. Okay, so this is, they took a different tactic here where they had a string accumulation in this second accumulation stage. So yeah. Oh, and that's something else I wanted to mention. Well, let's do it like this. Let's say, let's have our list equals list for num, comma, word, and tup list. List dot append word. Return string space dot join list. Okay. Right here on line 84, where I have selected for num, comma, word in tup list, right? This is like your, and that look familiar to like enumerating or using zip or something. Again, I could see this maybe being like like what the heck is going on there? Why can you just do that? And this is an opportunity to look to learn. We're iterating through a list of tuples. We can pull apart, we can unbox each of those tuples. So, right, if I just went through here and just did tup, right, for tup in tup list, print tup, well, yeah, I mean, this is not, you know, mind altering, you know, mind bending super code. There's nothing magic about this, I assume, right? This is very straightforward. I'm guessing if you know how a for loop works and you know what lists and tuples are, I'm guessing you could look at this and say, you know, this is a tuple. We iterate through a list of tuples, we're going to get tuples out. Anywhere I have a tuple, I can just say, I can index into it. So tup sub 0 is the number, tup sub 1 is the word, right? So I could say tup sub 0, or word equals tup sub 0. Nope. Try again, third time's a charm. Num equals tup sub 0, word equals tup sub 1. But, you know, why take up two lines when I could do it in one line? Num comma word equals tup gets tup sub 0 comma tup sub 1, right? So this assigns tup sub 0 to num and tup sub 1 to word, right? So first to first, second to second, last to last, right? So each position on either side gets the complementary position on the other side. So, right, this is a simple tuple unboxing. I don't need to do tup sub 0 and tup sub 1 because, you know, having this num and word equals a comma b thing, a comma b is a tuple. If I don't put the parentheses around it, Python's still like, that's a tuple because it's separated by commas. So I don't need to index into the tuple. I can just do the tuple directly. So anywhere where I encounter a tuple and I get to assign something to that expression where a tuple is being expressed and I get to assign it to something, anywhere that's happening, I can unbox it, including here, right? So I can save myself from doing this here and do it here. So for num word in tup list. And that's how enumerate works. That's how zip works. They're not lists of tuples. They're generators. Enumerate might not technically be a generator. Well, that doesn't matter. That's getting into the weeds. They're generators that, or iterators that iterate over some series, and each time, each one of their iterations, they give you a tuple back. So they give you a tuple of however many items they give back, and you can unbox that tuple right in your for loop. So that's why you can do that in enumerate and zip, and that's why you can do that here as well. So that's how that works. Cool. I think that's the last one. Got a few minutes left. You know, I think since somebody asked about like, what do we do if it has multi-digit a multi-digit, multiple digit thingy. What's that called? Multiple digits, gosh. In it. So we could do that over the last remaining time. Let me see if I can bust that out, just to give a more satisfying answer than do it yourself. Let's see if we're actually getting, looks like we're getting an empty string there. So let's put that in a list and make sure we're getting an empty string really quick. Bingo. Okay. Okay, so if it has a digit. So I think in this case, we might want to restructure this part of the code. We'll do num equals, this is weird. Let's call it digits is equal to a string. And let's just accumulate all. So if ch is a digit, we'll say digits plus equals ch. I'm going to have to do the append later, and we're going to have to get rid of the break in order to do that. So let's try that. I'm going to go back to returning tup list, just so I can monitor it. Okay. We don't have anything in it, of course. So let's just, I don't know, let's just do this. So I think I want to go get all the way through this for loop and then do int of digits and then word. Oh, and I should actually make a test. Invalid literal for int with base 10, which is an empty string. You know what? I actually don't need to make it an int. That is just an unnecessary step. Okay. Oh, but that is interesting because there are certain situations here. If we look like, oh, that's silly. So I need to create digits up here. So for word in text.split. Now, so it's kind of funny because it's a full little accumulator pattern inside of a full little accumulator pattern, right? So same thing, we create our empty thing right before our loop. and then we do our thing with the thing that we accumulated into. So I think that was what was going wrong. Okay. I know it doesn't have to be an int, but you know what? I'm just more comfortable with it as an int. Just like it better. Okay. This is great. It works, but I don't actually have a test that'll do this. So for the good of the people, let's see. I wonder for the good of the people, let's maybe just make this 60. And this, let's make this 347. So this will be for the of the people good. $60, 47. Oh, it's not really grammatical, but whatever. For the of the people good. Is this just going to work if I just do that? For the of the people good. Okay, so this works with multiple digits. Does that answer your question? Cool. Awesome. Cool. We can conclude class with that. I will turn off the recording and we can have questions. Yeah, you're welcome.